Today, we want to look at the integral of cosine squared x dx. This is actually from a broad category of integrals that we have to be familiar with. When we're integrating products of powers of trig functions, most of the time with sines and cosines, we can get away with some kind of substitution. All we need is an odd power of sine or an odd power of cosine, and then the problem just becomes substitution. Whichever we have an odd power of, make w equal to the other one. Then that odd power, or one factor of that odd power, can be the dw. We run into a problem and we stop being able to do substitution once we get to even powers of sines and cosines. And our prime target for this is going to be the integral of cosine squared x dx. We're going to first do this by parts, and then we're going to look at all the different ways that integrating cosine squared x by parts can go wrong. And then we're going to look at a better way for integrating even powers of cosines and sines. So let's take a look at cosine squared. The first thing that we want to do when we're integrating by parts is step 0. Make sure this is not a substitution. We have an even power of cosine, but no powers of sine. So I can't make w equal cosine because I don't have the dw. I don't have a factor of sine to be the dw. So substitution is not going to work for this problem. And since this is early in our integrating careers, our only other option is to do parts or trig identities, which is really the way. So let's think about how we can set this up with parts. The first step is to choose what parts we're going to use. So it could be that we put all the cosines in the dv part. But this isn't going to work because if I knew the dv has to be something we can integrate. And if I knew the integral of cosine squared x, I wouldn't be doing parts. I would just be writing down what the integral of cosine squared x is. So this won't work. If we knew what v is for this dv, then we'd not be doing parts. So that doesn't make any sense to put all the cosines in the dv area. So one of the things that we can do, what if we put all the cosines over here and just left dv to be 1 dx? So let's try this assignment of parts. Du is going to be 2 times a cosine to the first x times the sine, the minus sine of x dx using the chain rule. Over on the dv side, if dv is 1 dx, then v is x. Now, if we put together into the parts formula, if I go uv minus the integral of v times du, I'll have x times cosine squared. I'm going to do this on a separate line. So after doing parts, we do uv, so x times cosine squared x minus the integral of v times du. I'm going to factor the -2 out, and that'll become a positive 2. But then the integral that I have left over is x cosine x sine x. And this is worse than what we started with. If it was just the cosine and the sine, that would be no problem, but we've got this extra factor of x, which really messes things up. So we don't like this extra power of x. Extra factor of x. It doesn't fit in with the substitution. And if we split up with parts again, I don't know how to integrate x cosine. Well, I'd have to do parts to integrate just the x cosine x part. And substitution isn't going to work because if w is cosine, then dw could be sine because I've got odd powers of cosines and sine. But this x is going to be some kind of cosine inverse or sine inverse, and all of a sudden things are worse. So we don't like this secondary integral, so we're going to try something else. So this was attempt number 1. Here's attempt number 2. And we don't like the resulting secondary integral. So we're going to go on to attempt number 3. So this brings up a couple of things. I've got 2 factors of cosine. One thing that we can do is split the factors. I don't have to have all the cosine factors be in u or dv. It's possible to split up your factors. This is something that we haven't done so far in a parts problem. So we're going to try splitting the factors, see if that gives us something interesting. In particular, it'll keep this 1 from turning into an x and introducing x factors in our secondary integral. So du, the derivative of cosine is negative sine x dx, and the integral of cosine is sine. So v is sine x. So now I can put things into the parts formula. So the integral of cosine squared x dx is uv. So a cosine times a sine minus the integral of v times du. So I'm going to factor the negative out and make this plus. And sine times sine is sine squared. So now we just have to integrate sine squared. We had the 2 previous attempts on cosine squared where u is equal to 1 and dv is cosine squared. That wouldn't work because we don't know the integral of cosine squared. We tried switching u as cosine squared and dv as 1, but that introduced that factor of x, and we're trying to avoid making our secondary integral more complicated than the first one. So our new strategy has been to split the cosines, one factor in u and the other factor in dv. It's reasonable to think that this should work now. Maybe we should try, it's not going to work. Just spoiler alert, this isn't going to work, but it's a reasonable thing to try. So maybe we're going to try parts again for this sine, and u is going to be sine x, and dv will be sine x dx. Just following our plan. Then du, the derivative of sine is cosine, and the integral of sine is negative cosine. Oops, no dx on that one. So I end up with cosine x sine x plus then the parts formula for sine squared using the same strategy that we did before would be minus cosine x sine x minus the integral of cosine x times cosine x. So the negative cosine is going to make a positive integral, and we'll have cosine squared x dx. And now we have run into a problem. Because notice that these two terms, the cosine x sine x minus cosine x sine x, these two terms cancel out. And so we're left with the integral of cosine squared x dx is equal to the integral of cosine squared x dx. Which is not exactly a useful conclusion. So in that sine squared, splitting the sines, 1 power of sine for u and 1 power of sine to be dv, that strategy didn't work. So the splitting sines didn't work. Here's what we can do. So splitting the sines. Splitting the factors of sines didn't work. So we're going to do a different thing. We're going to apply a trig identity to replace the sine squared with cosine squared. The reason that this is going to work is that the integral of cosine squared is the integral that we're trying to find. So if I can produce a copy of integral of cosine over cosine squared over here in our secondary integral, then I can just add that term to the original and then divide by whatever the constant is. So here we are at attempt 3A. Where the integral of cosine squared x dx, I'm picking it up from, we have cosine x times sine x minus the integral of sine squared x dx. So rather than splitting the sines, I'm going to replace sine squared with 1 minus cosine squared. So sine squared is 1 minus cosine squared x. So I can split up my integral. I have the integral of this difference. So I can just write the difference of the integrals. So I have a cosine x sine x minus the integral of 1 dx. Minus and minus is plus the integral of cosine squared x dx. Plus the sine squared. So it'll be a minus. It was supposed to be a plus integral of sine squared. So we're subtracting the integral of cosine squared x dx. The reason that this is useful is that now I have an integral of cosine squared x dx on both sides of the equation, so I can add that to both sides of the equation. So if I add a copy of integral cosine squared x dx to both sides, I will end up with two integrals of cosine squared x dx is equal to cosine x sine x plus the integral of 1 dx. So if I add a copy to both sides, that cancels it out on the right and doubles it up on the left. Now I'll just integrate the 1 and divide by 2. Now we can divide by 2, and we get that the integral of cosine squared x dx is 1/2 of x plus 1/2 of cosine x sine x. Plus some constant. So one of the things that happened here was halfway through the problem, we put a trig identity in to get us through the rest of the problem. That should make us think maybe there was a trig identity that we could have used at the beginning to simplify the problem. That's not always the case, but it is sometimes. It's also sometimes the case, like when we're doing substitution, if you do parts is a process that might have to go in stages. You just have to do multiple parts. Substitution, one of the things that we need to know about substitution, if we're doing substitution and then later on in the same problem we have to do that another substitution, there's probably a bigger thing that we could substitute way back at the beginning to shorten the whole process. A similar thing happens here. We have cosine squared, we replace the sine squared with 1 minus cosine squared, specifically to get a copy of our original integral, another copy of integral of cosine squared that I can add to both sides and then just divide out by a constant. But there's another identity that we can use that simplifies things further. So here's attempt to number 4.
Professor Rich, you don't mind if I have a question, if you don't mind.
Mm-hmm.
On the this example where on the top, cosine squared x dx, how do you get to cosine x on the right with sine x?
That was from here. That's where we split the factors. U is cosine, dv is cosine. And so here we are doing that. This is the line I wanted to start from, because this technique where we split the signs, that didn't work. So now I want to go back to this line and try something else. So this is where I went back to, and then I started up again. And so that's why
In this case, on the right, cosine x is, which one is u, which one is v, you know? Does it count?
we made u cosine and dv cosine as well. This comes from this application of parts.
If this is the case, could you explain us on number two, Professor Lee? Number one, number two. Number two, we have the u cosine x, and how did you get to derivative, like du negative 2?
So in number two, u is cosine squared x. So the derivative of cosine squared is 2 cosine to the first times the derivative of cosine, which is negative sine x.
Oh, can you repeat that again, please, Professor Lee?
U is cosine squared. So the derivative is 2 cosine to the first, 2 cosine to the first, times the derivative of cosine, which is negative sine.
Oh, you kind of split it. So there's two of them, isn't it?
There isn't two of them. I took the derivative using the chain rule.
Oh, okay. I will review on that. Oh, thanks, Professor Lee. It kind of confused me.
So that the du is all, we always find du just by taking the derivative of whatever we chose to be u. So the derivative of cosine squared, we had to use the chain rule. The derivative of something squared is 2 times that thing to the first times the derivative of that thing.
One more thing on the right, on number two, dv, how you get 1 dx? Where is that coming from, you know?
The first step in doing parts is decide on what's u and what's dv. So I just took u to be the cosine squared, and then dv would just be the rest of it. And there's only the dx left over.
I got it. Thanks, Professor Lee.
So we're going to use a different identity at the beginning. We have the integral of cosine squared. And rather than use parts, we're going to use a trig identity at the beginning. We're going to use a double angle identity. So the double angle, one of the double angle identities for cosine says that the cosine of 2x is cosine squared x minus sine squared x. But cosine and sine are related by Pythagorean identities. So I could write this as 1 minus 2 sine squared x, or more useful for us, 2 times a cosine squared x minus 1. So this is the double angle identity for cosine. The cosine of 2x is 2 cosine squared x minus 1. What we can do is solve this identity for cosine squared, and then instead of integrating a power of cosine, I can just get away with integrating cosine of 2x, which is just going to be a negative 1/2 sine of 2x. So we're going to trade our cosine square. I'm going to solve this equation. It says cosine of 2x is 2 cosine squared x minus 1. We're going to solve this for cosine squared. So I'll take the cosine of 2x, we'll add 1, and then divide everything by 2. And I'm specifically solving for cosine. I'm not going to take the square root of both sides because I want to replace cosine squared in my integral. So now that I can replace cosine squared, this integral is going to actually be the integral of 1/2 plus 1/2 cosine of 2x dx. The reason that this is better is that we don't have a power on the cosine. It's just the cosine of 2x, and that's easily integrated with a chain rule. Or sorry, with integration by substitution. Now we can just go a term at a time. The integral of 1/2 is 1/2 x. The integral of a half cosine of 2x is a 1/4 sine of 2x plus c. So the integral of cosine of 2x will be 1/2 sine of 2x, and then the two 1/2s make a 1/4. Now we might look at this and say, this does not look like what we had before. I see the 1/2 x, but there's a 1/4, and there's a sine of 2x, which is not cosine x sine x. So the constant seems wrong, and it's a sine of 2x, not a cosine x sine x. But there's a double angle identity for sine as well. The sine of 2x is 2 sine x cosine x. So if I replace my sine of 2x with 2 cosine x sine x, the 1/4 and the 1/2 become a 1/2. So I get 1/2 x plus 1/2 cosine x sine x plus c. So the point is, all those identities that we may or may not remember, it's not important to remember precisely what the identities say. It is important to remember that the identities exist, because you can always look them up. So here's just the Google image search for double angle identities. And this is the first, and you can just click on the first image and it shows the double angle identities for sine and cosine and tangent. So it's not critical to remember what the double angle identities say, but it is helpful to remember that they exist. Once we can integrate even powers of cosine, we can now integrate products of powers of sines and cosines in any combination, because we can write everything as powers, even powers of cosine. So I can replace cosine squared with a half plus a half cosine of 2x. So if I have a cosine to the 4th x, I can just write the square of the sum of a half and a half cosine 2x. The idea is that cosine raised to a power is troublesome, or raised to an even power, but cosine of an even number times x is pretty easy to deal with.
Hey, Professor, could you talk about how you got 1/2 plus 1/2 cosine 2x?
Yeah, I just took my double angle identity, what says cosine of 2x is 2 cosine squared x minus 1. And then I added 1 to both sides. So cosine of 2x plus 1 is equal to 2 cosine squared x, and then divide by 2. Divide 2 cosine squared by 2, you get cosine squared. 1 divided by 2 is a half, and then 1 cosine of 2x divided by 2 is a half cosine of 2x.
Got it. Thank you.
Hardest part of calculus is all the algebra. Mostly because at this point in your mathematical career, you've passed an algebra class, but you're not necessarily fluent in algebra. You're still having to think about it a lot.
Also, how in the 1/4, like I know you just talked about this, but how did you get in the first place?
So that's from integrating a 1/2 cosine of 2x. So if we want to integrate 1/2 cosine of 2x to x, we can think of the 1/2 as just a constant multiple, but if we do the substitution on 2x, if w is 2x, then dw is 2 dx. So a 1/2 dw is dx. So this dx is being replaced with a 1/2 dw. And so the 1/2 that we started with and the half dw make the 1/4.
Okay, cool.
So this 1/2 and this 1/2 make the 1/4. This only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. All the while doing algebra that you still have to think about and remember some weird trigonometry facts. So this is very taxing on your memory. So you have to notice that the cosine squared, first of all, you have to know that even powers of sines and cosines are a problem because we can't integrate just with substitution. I don't have an odd power of cosine or sine to be the dw. Parts worked in the previous problem, but that's not the most efficient thing. We had to do some weird parts shenanigans. We had to do a trig identity and then move our original integral to the new copy of our original integral to one side so that we could divide by a constant. Since we're using trig identities, it's better to use a trig identity to get rid of a power of a trig function and trade it for a trig function to the first power, but have a constant times x, because that's easy to deal with. That's an easy integration by substitution. So for example, if we had to integrate the cosine to the 4th x, here's an even power of cosine. We can use the same identity. Cosine squared x is a 1/2 plus a 1/2 cosine of 2x. So that's just the double angle identity when it's solved for cosine squared. A half plus a half cosine 2x. And I can do the same thing. I can replace cosine squared with 1/2 plus 1/2 cosine of 2x. Since cosine to the 4th is just cosine squared squared, I can write my integral as a half plus a half cosine 2x squared. Now, this is still not where we need to be. I should multiply this out. If I can write things as terms, then maybe I should write things as terms. So just multiplying my integral out, I get the integral of 1/4 plus a half times a half is a fourth times 2 is a half, plus 1/2 cosine of 2x plus 1/4 cosine squared of 2x. So at this point, we've pulled up another cosine squared. But that's okay, because we have the double angle identity. If cosine squared x is 1/2 plus a half cosine of 2x, then cosine squared of 2x is just going to be a 1/2 plus 1/2 cosine of 4x. So now my integral can be written as a 1/4 plus a 1/2 cosine of 2x, that's no problem to integrate, plus 1/4 of a half plus a half cosine 4x. So now I have integral of, let's see, 1/4 and a half times a half. I should simplify this. This is going to be 1/8 plus 1/8 cosine of 4x. So I got a fourth plus an eighth. 2/8 plus 1/8 is 3/8 plus a 1/2 cosine of 2x plus 1/8 cosine of 4x dx. Now I've gotten rid of all my even powers of cosine because those are inconvenient. And now I could just integrate cosine of 2x. That's just going to be a 1/2 sine of 2x. And the integral of cosine 4x is just going to be a fourth sine of 4x. So integrating with respect to x, we'll have 3/8 x plus 1/2. The integral of cosine of 2x is a 1/2 sine of 2x plus 1/8 times the integral of cosine of 4x is a 1/4 sine of 4x. Now that we've integrated, we can type plus c and then clean up our fractions. This is not the only thing that we could have done. We could have just used parts. But this is how we deal, one of the ways that we deal with even powers of cosine. So this raises the question, like, well, which way is faster? Which way is faster is an irrelevant question, because this is not how we would go about finding the, if speed is the issue, then this is 100% not how we would deal with finding the integral of cosine to the fourth x. We would do something more like this. If speed is the issue, then this is not what we would be doing. Neither one of these things is what we would be doing. If speed is the issue and we don't have a computer, then I would argue that speed is not going to be the issue. You don't get to argue that speed is an issue and then say, but you don't have a computer. Because if you're trying to do this kind of work and you don't have a computer, it's not about the speed. It's probably about your employer not providing you with the tools that you need to be successful, in which case it's time to leave. Any questions?
Professor, so I kind of got confused to the cosine 2x squared part.
Uh-huh.
And like I'm not sure how you got 1/4 plus 1/2 cosine 2x plus 1/4 cosine squared 2x dx.
I just multiplied out the 1/2 plus a half cosine of 2x. So first, outer, inner, and then last. And then the 1/4 and the 1/4. Oops, there it is. Now 1/4 and 1/4 is a half. When we combine like terms. All right. That's going to do it for today. I know we spent a lot more time doing trig stuff than we did doing parts, but the integral of cosine squared is presented in the parts section, and there's no supporting arguments about why this is not the only way of approaching this problem. It makes sense because this section is about parts, but I think it bears commenting that there's other ways to deal with even powers of cosine. In particular, was parts still going to be the way with cosine to the 4th? What would that look like if we used parts? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.